Welcome to this video. Today, we'll explore the problem number 1183, titled Maximum Number of Ones. We'll break down the problem, discuss potential approaches, and walk through the solution step by step. Let's get started. In this problem, you are tasked with working on a binary matrix defined by its width and height. Each cell in this matrix can either be a 0 or a 1. Additionally, you are given a side length, which defines the dimensions of a smaller square submatrix, and a value maxens, which sets the maximum number of ones that can appear within any submatrix of size side length x side length. Your objective is to determine the maximum number of ones that can be placed in the entire matrix while ensuring that every side length x side length submatrix adheres to the maxens constraint. For example, if side length is 2 and maxens is 1, no 2 by 2 submatrix can contain more than one 1. The input specifies width, height, side length, and maxens, and the output is the maximum number of ones that satisfy these conditions. To understand the problem better, let's look at some examples. In the first example, the matrix dimensions are 3 by 3, the side length is 2, and maxens is 1. This means that in any 2 by 2 region of the matrix, there can be at most one 1. A possible configuration that satisfies this is having ones placed diagonally 1, 0, 1 in the first row, 0, 1, 0 in the second row, and 1, 0, 1 in the last row. Each 2 by 2 submatrix in this configuration has at most one 1, and the total number of ones in the matrix is 4. Therefore, the output here is 4. Now let's look at a slightly different example. Here, the matrix is still 3 by 3, but the side length remains 2, and maxens is increased to 2. This means that in any 2 by 2 region, we can now have up to 2 ones. A valid configuration for this scenario could have the first 2 rows filled as 1, 1, 0 and 1, 1, 0, with the last row entirely zeros. In this arrangement, each 2 by 2 submatrix is allowed to have up to 2 ones, and the total count of ones in the matrix becomes 6. As a result, the output for this example is 6. In the third example, the matrix size increases to 4 by 4, the side length becomes 3, and maxens is set to 4. This means that in any 3 by 3 submatrix, we can include up to 4 ones. Since the constraint allows up to 4 ones in any submatrix and the side length is large relative to the matrix size, it becomes possible to fill the entire 4 by 4 matrix with ones. In this case, the total number of ones in the matrix is simply the total number of cells, which is 16. Thus, the output for this example is 16. Finally, let's review some edge cases to consider. If maxens is 0, the matrix cannot have any ones at all, and the output will always be 0. On the other hand, if maxens equals side length squared, it means every submatrix can be completely filled with ones, so the output will simply be the total number of cells in the matrix, which is width times height. For a single-cell matrix, where width, height, and side length are all 1, the output depends on whether maxens is 0 or 1. Lastly, it's important to test the solution with large matrix sizes close to the upper constraint of 10,000 by 10,000 to ensure that the implementation remains efficient and adheres to the problem's constraints. To tackle this problem, we first considered a brute force approach. The intuition here is straightforward: generate all possible binary matrices of size height x width, then calculate the number of ones in every possible submatrix of size side length x side length, ensuring that the count of ones doesn't exceed the given maxens. Among these configurations, the goal is to select the one that maximizes the total number of ones. However, there are significant challenges with this approach. The number of possible configurations grows exponentially with the size of the matrix, making it computationally infeasible for larger inputs. On top of that, checking every submatrix for each configuration adds even more complexity. In terms of time complexity, this approach has an exponential growth rate of 2 height asterisk width asterisk height asterisk width 2, which is simply unsustainable for larger matrices. The space complexity is also proportional to the matrix size, height asterisk width. While this method is conceptually simple, it is impractical for the constraints of the problem, so we need a more efficient solution. Instead of the brute force approach, we shift our focus to an optimized solution that leverages the repetitive nature of the problem. The key insight here is recognizing that the side length x side length submatrices repeat periodically across the larger height x width matrix. This means that instead of analyzing the entire matrix, we can concentrate on this smaller side length x side length block, as it determines the configuration of the entire matrix. By doing so, we reduce the problem to a much smaller and more manageable size. The next step is to calculate the contribution of each cell within this sidelength x sidelength block. For example, a cell at position I, j, contributes to all submatrices that include this cell, and the total contribution depends on how many times the block is repeated across the matrix dimensions. Cells with higher contributions are more valuable, so we prioritize placing ones in these positions. To implement this, we compute the frequency of each cell's contribution across all submatrices, sort the cells by their contribution in descending order, and then place ones in the top Maxence cells. This reduces the complexity significantly. The time complexity of this approach is O, sidelength (2 asterisk log, sidelength (2), for sorting, and the space complexity is O, sidelength (2), to store the frequency data. This optimized approach is both efficient and scalable, making it suitable for the problem's constraints. The core idea revolves around leveraging the periodic structure of the sidelength x sidelength block. The critical observations here include recognizing that configurations outside this block are redundant, reducing the problem to operations on a smaller grid. Furthermore, the contribution of each cell can be pre-computed, which simplifies the process of identifying the most valuable cells. Sorting these cells by their contribution ensures that we maximize the number of ones in the final configuration. Compared to the brute force approach, this method avoids exponential growth in complexity, making it computationally feasible even for larger matrices. By focusing only on the essential subset of the problem and using pre-computation and sorting, we strike a balance between efficiency and optimality. This strategy was chosen because it guarantees an optimal solution while staying within polynomial time complexity, making it vastly superior to other alternatives. The optimized approach does involve some trade-offs. While it sacrifices the simplicity of the brute force method, it gains significant efficiency by requiring pre-computation and sorting. This additional complexity is necessary to handle larger inputs within the problem's constraints, ensuring the solution remains practical. By focusing on the repetitive structure of the sidelength x sidelength block, we significantly reduce computational overhead. Prioritizing cells with the highest contributions allows us to achieve an optimal solution without exhaustively evaluating every possible configuration. In conclusion, this approach effectively balances efficiency with clarity, leveraging the periodic nature of the problem to simplify the solution space. By concentrating on the most impactful cells in the sidelength x sidelength block, we ensure that the solution is both optimal and scalable, meeting the requirements of the problem efficiently. To start, the problem at hand is to construct a binary matrix of size height x width that adheres to specific constraints. Specifically, the matrix must be structured so that the number of ones in any submatrix of size sidelength x sidelength does not exceed a given maximum value, called Maxence. The objective is to efficiently generate this matrix while satisfying these constraints. One intuitive but naive solution is the brute force approach. This involves generating all possible binary matrices of size height x width. Since each cell in the matrix can either be 0 or 1, the total number of configurations is 2 raised to the power of the total number of cells. For example, a 2 by 2 matrix has 16 possible configurations. Once we generate these matrices, we iterate through each one and calculate the number of ones in all possible submatrices of size sidelength x sidelength. This method is conceptually simple, but its inefficiency becomes apparent as the matrix size grows. After generating all possible matrices, the next step in the brute force approach is to validate each submatrix. For every submatrix within a given binary matrix, we count the number of ones and check whether this count exceeds the Maxence constraint. If even a single submatrix violates this condition, the matrix is discarded as invalid. On the other hand, if all submatrices satisfy the constraint, the matrix is stored as a valid solution. Finally, we output either the set of all valid matrices or the total count of these matrices, depending on the requirements of the problem. While this approach ensures correctness, it has significant drawbacks. The exponential complexity of generating all configurations makes it computationally infeasible for larger matrices. Additionally, because submatrices often overlap, there is a lot of redundant computation when counting ones in overlapping regions. These inefficiencies highlight the need for a more optimized solution, one that avoids generating all configurations and focuses directly on placing ones in an optimal way. To address the inefficiencies of the brute force method, we shift our focus to an optimized approach. Instead of generating all possible binary matrices, we aim to strategically determine where to place ones in the matrix. The goal is to maximize the number of ones in the top left submatrices of size sidelength x sidelength while adhering to the maxens constraint. To achieve this, we assign a weight to each cell based on how many submatrices it contributes to. Cells that are central or located in overlapping regions of submatrices typically have higher weights. Using a max heap or sorting mechanism, we prioritize placing ones in the cells with the highest weights. After determining the priority of cells, we iteratively place up to maxens ones in the top weighted positions. This ensures that the constraints are satisfied without the need for exhaustive validation. Once the ones are optimally placed, the resulting binary matrix is constructed and returned as the final solution. Now, let's analyze the complexity of these approaches and consider potential edge cases. The brute force solution has a time complexity of 2 to the power of height asterisk width, which is prohibitively expensive for practical use. In contrast, the optimized approach has a significantly reduced complexity. Calculating weights for each cell and sorting them by priority takes height asterisk width asterisk log, height asterisk width, while placing maxens ones adds an additional maxens. Together, this makes the optimized solution much more efficient. In terms of edge cases, if maxens is 0, the output should be a matrix filled entirely with zeros. If side length exceeds the smaller dimension of the matrix, submatrices cannot fit, and the solution simplifies accordingly. Lastly, for a 1x1 matrix, the solution reduces to determining whether the single cell is 0 or 1, depending on the constraints. These considerations ensure the solution is robust across various scenarios. The optimized approach can be implemented efficiently using a combination of weighted calculations and sorting. First, we calculate the weight of each cell, which represents the number of submatrices that include this cell. This is accomplished by iterating over the possible bounds of submatrices and incrementing weights for each overlapping region. Then, we sort the cells in descending order of their weights. After sorting, we construct the binary matrix by placing ones in the top maxens cells with the highest weights. The remaining cells are left as zeros. By focusing on the most critical cells, we ensure that the constraints are satisfied without redundant computations. In summary, this method transitions from the brute force approach to a weight-based strategy, leveraging insights about overlapping submatrices to drastically reduce time complexity. This makes the solution not only computationally efficient but also practical for real-world problem sizes. This code solves the problem of maximizing the number of ones in a binary matrix under the given constraints. The matrix is divided into a repeating pattern of side-length x side-length blocks. Each position in this block contributes to multiple positions in the original grid. First, the code calculates the contribution of each position within the side-length x side-length block to the entire grid. The contribution is determined by counting how many times the block's position overlaps with the grid, based on the grid's dimensions, width and height. For each position, I, j, its contribution is proportional to how many full blocks fit in the vertical and horizontal directions starting from I, j. Next, these contributions are stored and pushed into a max heap, implemented using Python's heap with negative values to simulate a max heap. This allows us to efficiently retrieve the positions with the highest contributions. Finally, the algorithm retrieves the top maxens contributions from the max heap and adds them to the result. This ensures that the sum of contributions, i.e., the number of ones in the matrix, is maximized while respecting the maxens constraint. The code is efficient, as it avoids constructing the full grid explicitly and focuses only on the smaller block of size side length x side length. This makes the solution suitable for large values of width and height. Here, we start by importing the necessary packages and defining our class and method, maximum number of ones. The goal of this method is to calculate the maximum number of ones that can be placed in an NXM grid while respecting the given constraints. To achieve this, we first create a map to store the contribution count for each cell in a side-length x side-length block. The contribution of a cell represents how many times that cell can appear in the grid when the block is tiled repeatedly. We then calculate the contribution for each cell by iterating through the rows and columns of the block using nested loops. For each cell, I, j, the contribution is calculated based on how many times it can fit horizontally and vertically in the grid. These contributions are stored in the contribution map, where the key is the cell's linear index, and the value is its contribution count. Afterward, we use a priority queue, implemented as a max heap, to store all the contribution values. This will allow us to efficiently extract the cells with the highest contributions. To determine the result, we extract the top maxens contributions from the max heap. Using a loop, we repeatedly pull the highest value from the priority queue and add it to the result. This ensures we prioritize the cells that contribute the most to the total number of ones in the grid. Once we have added up to maxens contributions, we return the final result. This concludes the implementation, where we efficiently compute the maximum number of ones by leveraging the grid's repetitive structure and prioritizing the cells with the highest contributions. To solve this problem, we start by creating a contribution dictionary. The goal here is to calculate how many times each position within the block defined by the side length contributes to the overall grid. For this, we iterate over all positions I, j in the 2x2 block, and for each position, we use the formula height I1 / side length plus 1 asterisk with j1 / side length plus 1 to determine its contribution. For example, for position 0, 0, this formula evaluates to 2 asterisk 2 equals 4, meaning this position contributes 4 times to the larger grid. Similarly, position 0, 1 contributes 2 times, 1, 0 also contributes 2 times, and 1, 1 contributes just once. This gives us the contribution dictionary 0, 0, 4, 0, 1, 2, 1, 0, 2, 1, 1, 1. Next, we push these contributions into a max heap, storing their negative values since heaps in Python are by default min heaps. The heap ends up in the state -4, -2, -2, -1. Which allows us to efficiently extract the largest contributions later. Now that we have the heap, we proceed to extract the top maxens contributions. Since maxens is 2 in this example, we extract the 2 largest contributions from the heap. The first extraction yields -4, which we convert back to its positive value 4. The second extraction gives -2, which becomes 2 when converted back. Adding these values together, we find that the maximum number of ones that can be placed in the grid is 4 plus 2 equals 6. Moving to a larger grid example, we now have width equals 5, height equals 5, side length equals 3, and maxens equals 4. In this case, we follow the same process, iterating over the 3x3 block to calculate contributions. For instance, position 0, 0 contributes 2 asterisk 2 equals 4, and position 0, 1 contributes 2 asterisk 1 equals 2. This builds a partial contribution dictionary, starting with 0, 0, 4, 0, 1, 2. After constructing the contribution dictionary for the larger grid, we push all contributions into a max heap and extract the top maxens values. Since maxens is 4, we extract the 4 largest contributions and sum them to determine the final result. Finally, let's consider an edge case where the grid is quite small, width equals 2, height equals 2, side length equals 2, and maxens equals 1. In this scenario, each position within the 2x2 block contributes exactly once because the grid perfectly matches the block size. The contribution dictionary is 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. The max heap consists of -1, -1, -1, -1, and extracting the single largest value gives 1. Thus, the output is simply 1, demonstrating how the solution adapts to edge cases effectively. Here, we analyze the time complexity of the solution step by step. First, we calculate the contributions for each position in the side length x side length block. This involves a nested loop that iterates over all positions, performing arithmetic operations at each step. Since the total number of positions is side length (2) and each operation takes constant time, this step has a complexity of O side length (2). Next, we build a max heap to store these contributions. Inserting each of the side length (2) contributions into the heap takes logarithmic time, so the complexity of this step becomes O side length (2) asterisk log side length (2). Finally, we extract the top maxens contributions from the heap. Each extraction operation takes logarithmic time, and in the worst case, we perform up to maxins extractions. If maxins is small compared to side length caret 2, this step becomes negligible, but its complexity is O, maxins asterisk log, side length caret 2. Now, combining all these steps, the total time complexity of the solution is O, side length caret 2 asterisk log, side length caret 2, plus maxins asterisk log, side length caret 2. For most practical scenarios, where side length caret 2 is significantly larger than maxins, the dominant term is O, side length caret 2 asterisk log, side length caret 2. Shifting to space complexity, the solution requires a dictionary to store contributions for each position in the side length x side length block. With side length caret 2 entries in each entry consisting of a tuple and an integer, the space used by the dictionary is O, side length caret 2. Additionally, the algorithm uses a max heap, which also stores up to side length caret 2 contributions, resulting in a space complexity of O, side length caret 2, for the heap. Finally, a few auxiliary variables like resultant value require constant space, which adds just O1 to the overall space complexity. The total space used by the auxiliary variables is negligible, so the space complexity remains dominated by the dictionary and the heap, giving us O, side length caret 2, overall. Comparing this to a brute force approach, the naive method would involve constructing the entire grid of size width x height and calculating contributions directly by iterating over all positions. This would lead to a time complexity of O, width asterisk height, and a space complexity of O, width asterisk height, for storing the grid. For large values of width and height, this approach becomes computationally expensive and impractical. In contrast, the optimized approach focuses only on the side length x side length block, significantly reducing both time and space requirements. Instead of constructing the entire grid, it calculates contributions mathematically, which is far more efficient. The time complexity of the optimized solution is O, side length caret 2 asterisk log, side length caret 2, which is much better than O, width asterisk height, for large grids. Similarly, the space complexity is reduced to O, side length caret 2, which is far smaller than the O, width asterisk height, of the brute force approach. In summary, this solution leverages mathematical insights and heap optimizations to achieve substantial improvements in efficiency, making it well suited for scenarios with large grids and high computational constraints. When solving this problem, there are several common mistakes to watch out for. First, ignoring edge cases is a frequent issue. For example, matrices that are very small, like a 1x1 matrix, or those filled entirely with zeros or ones, often expose boundary condition errors that might otherwise go unnoticed. Another common pitfall is incorrect prefix sum calculation. When working with prefix sums, off-by-one errors can easily occur if the formula for retrieving submatrix sums isn't carefully verified. It's also critical to account for the problem's constraints. For instance, if the matrix size is extremely large, say 10,000 by 10,000, a brute force solution will be too slow and exceed time limits. In these cases, you need to optimize using more advanced techniques. Additionally, if you're using a sliding window approach, overlapping regions in the matrix can lead to double counting or missed elements, so handling overlaps correctly is essential. Lastly, hard-coding values like matrix dimensions or specific thresholds can make your solution inflexible and prone to failure when the inputs change. Always write dynamic, adaptable code to handle varying scenarios. Now, let's focus on insights for interviews. In a technical interview, optimization is a key factor. Interviewers often expect you to start with a basic brute force solution and then refine it for better time and space efficiency. Be ready to articulate the trade-offs involved and explain how techniques like prefix sums or dynamic programming can improve performance. Clear communication is equally important. Walk the interviewer through your thought process, especially how you plan to optimize your approach. Demonstrating awareness of edge cases is another crucial skill. Highlight these cases as you code, and show how you proactively address potential pitfalls. Additionally, recognizing patterns can save valuable time. For instance, this problem is a classic example of matrix-based optimization, which includes concepts like prefix sums and sliding windows. Recognizing such patterns allows you to quickly adapt previously learned techniques. To further prepare, you might want to explore related problems such as LeetCode 304's range sum query 2D, LeetCode 221's maximal square, or LeetCode 85's maximal rectangle, as these share similar concepts and can deepen your understanding. Finally, let's discuss alternative approaches to solving this problem. The brute force method, while straightforward, involves iterating through all possible submatrices, making its time complexity O, n to the power of 4. It's simple and useful for small input sizes but becomes impractical when dealing with large constraints. A more efficient option is the prefix sum method. By pre-computing prefix sums, you can retrieve submatrix sums in constant time, reducing the overall complexity to O, n squared, for most queries. However, this approach does require extra memory to store the prefix array, so memory usage should be considered. Another technique is the sliding window approach, which is especially effective for fixed-size submatrices. By avoiding redundant computations, this method is excellent for scenarios where you need to maximize or minimize submatrix sums. Lastly, dynamic programming is a powerful tool for variations of this problem that involve specific conditions, such as finding the largest square submatrix. It systematically builds solutions to smaller subproblems, making it an optimal choice for these kinds of tasks. Each of these methods has its strengths, so the best approach depends on the problem's constraints and requirements. Thank you for sticking with us. Today, we covered the maximum number of ones problem, explored its challenges, and discussed key takeaways. Remember to keep practicing and refining your skills. If you found this helpful, don't forget to support the channel. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!